And pause. All right, good morning. Let me see if I can get rid of this here. Oh, guess not. All right. So yeah, thanks very much for the introduction. I'm really excited to be here today. I've had the great fortune to work on a number of exciting problems over my career so far. And I have to say, this one is probably my favorite. So I hope I can describe to you today why that is. And it's also really good timing because this paper describing this work just came out 2 weeks ago. So today I want to talk about tiny earthquakes. And, especially coming from the USGS, I think we know that it's really the big earthquakes that we care the most about. These are the earthquakes that, sometimes kill people, damage buildings or other infrastructure. But I'm going to argue today that sometimes it's the tiniest earthquakes that can tell us the most about these big earthquakes. And sometimes we can use these tiny earthquakes to tell us things that we can't see from the big earthquakes. So I'm going to show how these tiny earthquakes can illuminate hidden plate-bounding faults and how they can help us understand the tectonic puzzle that we have at the Mendocino Triple Junction. So I will show that these bursts of low-frequency earthquakes in this area are generated by dipping strike-slip motion, and describe how this implies that there is a piece of partially subducted oceanic crust that has become stuck to the Pacific plate and is essentially being dragged northward 20 kilometers beneath Western North America, trailing behind the northward migrating Gorda plate. Okay, so the Mendocino Triple Junction, I would say, is really the keystone of Western US tectonics. I mean, this is the place where the Pacific, the Gorda, and the North American plates come together. And it's also the place where the San Andreas Fault meets the Cascadia subduction zone. So not surprisingly, it's also a place where we see a lot of earthquakes, including several recent earthquakes, including there was a 2021 magnitude 6 doublet. A year later, 2022, magnitude 6.4 Ferndale earthquake. And 2 years after that, just about a year ago, there was the magnitude 7 offshore Cape Mendocino earthquake. And today I'm going to talk about the implications of this little zone of tiny earthquakes located nearby. Okay, so before I talk about the tiny earthquakes, I'll just give you a little quick overview of the bigger earthquakes in this area. So I really got pulled into the Mendocino Triple Junction just over 4 years ago when this earthquake, or earthquakes, depending on how you look at it, happened. So this was a study led by my colleague Will Yeck, and it showed that this earthquake initiated with slip on the offshore Mendocino Fault with a magnitude 6.1 earthquake. 11 seconds later, that triggered essentially a separate earthquake onshore and much deeper within the subducting Gorda slab. A year after that was the magnitude 6.4 Ferndale earthquake, which was a strike slip earthquake within the subducting Gorda slab. I don't have time to get into the details of this, but this is our cartoon of what happened. The co-seismic slip essentially tearing that subducting slab. And then, interestingly, there was post-seismic slip that seems to have occurred on the subduction interface itself. So I think this is important in showing that how these different fault types or fault systems that we often treat separately can actually interact. And then just over a year ago was the 2024 magnitude 7 Cape Mendocino earthquake. I have not worked directly on this earthquake, but there are already a couple of papers that have come out looking at the slip, which may have been super shear in this earthquake. So we really have a lot of large earthquakes at the Mendocino Triple Junction. But like I said, the tiny earthquakes can sometimes tell us things that the big earthquakes can't. And so there are a few reasons for this, but mostly it comes down to numbers. For every magnitude 7 that we see on Earth, we get about 1,000 magnitude 4 earthquakes, about 1 million magnitude 1 earthquakes, and about 10 million magnitude 0 earthquakes. So for the purposes of this talk, those tiny earthquakes are these magnitude 1, magnitude 0 type earthquakes. And there are just a lot of them. So roughly, these are the numbers of events that you would get globally in about a month. So these tiny earthquakes can show us a lot of things. One is that they can show us the three-dimensional fault geometry, and they can sometimes show this before, sometimes after the big earthquakes happen. So that's important. The more that we understand about the fault networks, the better we can do forecasting future events and understanding how these faults interact. Small earthquakes can also show us where faults are creeping and how this creep evolves with time. So in the lower right is an example from the San Andreas Fault near Parkfield, showing these kind of bursts of creep that have been observed there. And so these are typically, the earthquakes used in this study, I believe, were around magnitude 2. But if we go to even smaller magnitudes, so these are some of these low frequency earthquakes. And these are around magnitude 0. And so actually, the smaller the earthquakes are, the better resolution we can get for how this slip evolves in space and time, because the smaller earthquakes represent a smaller increment of slip. So we have more of them and we can see we have more frequent observations of what's happening. So yeah, the tinier the better for this situation. Okay, so now I want to say just a little bit more about this specific kind of tiny earthquakes. It's low frequency earthquakes. So low frequency earthquakes are part of a tectonic tremor signal. This is a famous plot from just over 20 years ago, showing the blue dots are GPS positions from Vancouver Island, northern Cascadia, showing the overall eastward motion. But every 14 months or so, with these red arrows, that motion is reversed. This is modeled to be slow slip on the subduction interface, down dip of the main seismogenic zone. And each of these slow slip events is accompanied by a burst of tremor, which is shown as the black bars. So this is a long duration ground vibration that looks something like this plot in the lower left. The same kind of thing happens in Southwest Japan. In this case, the slow slip events are a bit smaller. They're detected on creep meters, but we also see these bursts of tremor accompanying these slow slip events. So I said tremor is a bunch of tiny earthquakes. But how do we know that? Well, it turns out that some bits of tremor are a little bit more impulsive and can occasionally be identified and located like typical earthquakes. So these were termed low frequency earthquakes, or LFEs. So I had the good fortune to work on this problem many years ago as part of my PhD work. What we found was that even during periods where there were no obvious LFEs, we could use matched filter analysis. So we're cross-correlating waveforms, and we could see that the same waveform signature was repeating over and over. And not only that, but using multiple LFE templates, multiple slightly different waveform signatures, we could see that the tremor is migrating in space over time. So tremor and LFEs at this point have been observed on numerous major plate boundary faults. Most of these are in subduction zones, but some are also on strike slip faults like the San Andreas Fault or the Alpine Fault in New Zealand. So in these locations, tremor and LFEs have been interpreted to represent shear slip. Similar to what I was mentioning in Cascadia, it's slip that's usually down dip from the main seismogenic zone, although sometimes up dip as well as in some of the subduction zones. Okay, so many of you are probably familiar with tremor in Cascadia. We see these dark blue dots are showing this long band, nearly continuous band of tremor activity that occurs down dip the seismogenic zone in Cascadia, all along the margin. And a few years ago, a paper by Aaron Weck pointed out that there's this odd little zone of tremor that's sticking out to the west from this main band right at the southern edge of Cascadia. But no one had really dug into this zone of tremor. So when we started out on this project, our goal was to figure out what the heck is going on with this weird zone of tremor that's sticking out where tremor really shouldn't be. So we started by looking at a few times with identified tremor activity in this area. Now, like I mentioned, tremor is a pretty messy signal. It's often pretty difficult to identify individual events in the tremor. So even though we think this is made up of a bunch of tiny earthquakes, these earthquakes often overlap and they're low amplitude, so it gets really hard to separate them out. But what we can do is we can just take a bit of this tremor activity. So here's an example highlighted in blue. We can cross-correlate it through a long time period of continuous seismic data. So in this case, we can cross-correlate it through about 4 years of continuous seismic data. We can find the most similar events during that time period. We can stack them together to improve the signal to noise, and we can repeat this process. And if we do this a couple of times, we go from this situation on the left, which just looks kind of like garbage, to the situation on the right, which looks like something seismologists would be much more comfortable with. And not only can we go improve the signal to noise, but we can add stations that didn't record the initial event and really expand our network of observations. So this is really the key to this kind of analysis, because once we have this template, we can detect really tiny earthquakes that are hidden in the noise. Earthquakes that have a signal to noise ratio less than 1 that you can't see, as any kind of amplitude increase, but that you can detect using a matched filter with many channels of data. And not only that, but we can identify phase arrivals, P waves and S waves, and use those to locate the sources, like we would with a traditional earthquake. So this is an example of one family of low frequency earthquakes. In this zone, we've in total located 27 different families. We first located using just a grid search technique. This is one of the a bit shallower sources among the ones that we see, is about 24 kilometers depth. We can get those initial locations, and then we can relocate things using a double difference technique and also with waveform cross correlation. So we did that. We located it together with the seismicity so that we could reference the two together. And this is the zone where the LFEs locate in the diamond shapes there. So it looks like the LFEs are kind of spread out, but if we look kind of in a 3D view, we can see that they're aligned along, what's plausibly a single structure. So if you look at this upper right plot, viewed from above and from the southwest, you can see that the sources are relatively well aligned. They're located between 22 and 29 kilometers depth, so a bit shallower than traditional Cascadia tremor and LFEs, but kind of similar to the San Andreas LFE depths. And they're actually adjacent to this, to a zone of micro earthquakes, which will become important later. So those micro earthquakes are located slightly shallower, but kind of on the western edge of where the LFEs are located. And one of the interesting features of this, again, I'll come back to this as well, but there's this gap between all of these earthquakes, or most of these earthquakes to the north, are earthquakes that are occurring within the subducting Gorda slab. These are interslab events. Then we have this gap, and then we have this zone, including the LFEs, and this kind of little zone of microseismicity there. Okay, so I won't say too much about this, but just briefly, these LFEs occur in very short, frequent bursts. So over the long term, it looks like almost like a straight line. There's some variations in network performance that may cause some slight deviations there, but basically they're active, relatively continuous. And this is quite different from that earlier plot that I showed, showing in northern Cascadia these major episodes that occur every 14 months and relatively quiet in between. So if we zoom in just on that little upper right corner there, you can see the little bursts of activity happening about every 2 days in this zone. Another feature of these events is that they're strongly tidally modulated. So on the left is an example family. This plot is showing the Schuster statistic, but it's basically a measure of how much power there is in these particular frequencies. So we see peaks that correspond to prominent tidal frequencies, and especially when we combine all the families. And again, this will be important in just a minute. Okay, so let's get back to this gap. So remember that there's this gap in seismicity just north of the low frequency earthquakes. It turns out this corresponds to a very prominent low P wave velocity zone. So this is a slice at 27 kilometers depth. I don't think it'll let me get rid of this, but so yeah, this gap corresponds to this low velocity zone, and we see this high velocity zone to the south. So the LFEs are on this velocity boundary, but it's kind of a weird one that there's a high velocity zone to the south. We do see the Gorda slab up here, but somewhere in between the LFEs and the Gorda slab, there is this low velocity channel. So this kind of feeds into the question, people have been debating for decades, where actually is the southern edge of the Gorda slab or the southern edge of subduction in Cascadia? And so each of these green lines is a different estimate from a different study, and they range over a pretty broad region. But within that range are these low frequency earthquakes. And, I showed earlier that low frequency earthquakes tend to occur on these plate bounding faults. These particular ones have frequent rapid recurrence every couple of days. This looks a lot like the kind of behavior that we see on the San Andreas Fault, which we know is moving at a few centimeters a year. This is not the kind of activity that you get on just some minor, very slow moving fault. This is really suggestive of a major plate bounding fault. So perhaps the LFEs are showing us where the southern boundary of subduction actually is. So in addition to the location of the edge of subduction, a big question in Mendocino tectonics has been what is happening at the southern edge of the subduction zone. So this is a diagram, showing how this all formed about 30 million years ago. The the spreading center of the Farallon slab encountered the trench. That's when the San Andreas Fault started to be created. And that's when you created the triple junction. So one idea that's been out there has been that as the Gorda plate is subducting, but it's also moving to the north. And as it moves to the north, it may essentially leave this gap where hot asthenospheric mantle may upwell and fill that zone. A competing hypothesis is that immediately south of the triple junction, rather than there being a slab gap, that there's this fragment of former Farallon, of the former Farallon plate that has partially subducted, it's stalled, and then it's become attached or captured by the Pacific plate. So this is an idea that's been out there since the 90s. Papers by Kevin Furlong have talked about this idea over the intervening decades. This is from a recent paper in 2024. But there hasn't been any evidence to show how the plates are moving down there in the lower crust zone. So what's actually going on? The problem is, like I said, we don't have any direct evidence of what the motion is down there. And so perhaps the LFEs could provide that if we could get the slip orientation. So this plot on the right is hypothetical of if we take the orientation that we see the LFE hypocenters align and we project different combinations of relative plate motion. These are the kinds of focal mechanisms or motion that we would see from the LFEs. So if it's, for example, relative motion between the Gorda and the North American plate, as you might expect if it's a slab window or if there's deep North American crust to the south, you get normal faulting. You might get oblique reverse faulting if it's relative motion between North America and the Pacific plate. Or you might get this kind of dipping strike slip motion if it's relative motion between the Pacific and the Gorda plate. So if we could determine the LFE slip orientations, we could go a long way toward solving this question. So unfortunately, that turns out to be kind of a tough thing to do. So this is one of the best LFE families, the stacked waveform template. You can see P waves there. The orange bars are marking the P wave picks that were used for location. A few of these stations, you can probably get a reasonable estimate on what the first motion polarity is. So, the usual way to get focal mechanisms for earthquakes is for small earthquakes at least, is by looking at the P wave first motions. But it turns out it's really hard to get reliable estimates of P wave first motions on enough stations to constrain a focal mechanism. Believe me, I tried and failed. So we need to do something else. These emergent arrivals just make it really difficult to determine first motions. But we might be able to use a different technique. So the figure on the left is from a study I worked on several years ago to look at ways that we could get relative polarities between two earthquakes by using the cross correlation between their waveforms, and in particular, using the fact of whether the peak absolute value cross correlation was positive or negative. If it's positive, we say these two events have the same polarity. If it's negative, we say they have opposite polarity. And this tends to be a noisy measurement, but that is counteracted by the fact that you have a lot of opportunities to make this measurement. You can look at lots of different pairs of events, and you can kind of boil all that down to get a reliable estimate. So like I mentioned, we do have this zone of microseismicity of small earthquakes up to about magnitude 3 that's just adjacent to the LFE activity in this area. And so what if we tried to use the waveforms from those earthquakes and cross-correlated them with the stacked waveforms from the low-frequency earthquakes? So it turns out this works relatively well. So the plot on the right is showing waveforms from one particular comparison earthquake plotted on top of the stacked waveforms from this family of low frequency earthquakes. I've color coded the waveforms with blue indicating compressional first motions and red indicating dilatational first motions. So this comes from first, whether the earthquake had compressional or dilatational first motions, and second, whether the correlation is positive or negative. So combining those two things, we can make an estimate of whether the LFE P wave first motions are compressional or dilatational. And again, this is a noisy measurement, but we have lots of opportunities to make this. In this case, we used 22 comparison earthquakes. We only used some of the earthquakes that were closest to the LFEs. We have 27 different families. We have 72 different channels of seismic data that we're considering. So this is 42,000 potential measurements. Now, we don't make nearly that many successful measurements, but we make enough that we can start to boil it down and get a reliable estimate of the focal mechanism. And so this is what that looks like. I plotted all of the polarity observations here. The pluses are compressional first motions. The circles are dilatational first motions. And it's not perfect, but this is the best fitting focal mechanism. And one thing that's important to note is that this particular nodal plane here is very close to the estimated alignment of the LFE hypocenter. So the strike is almost identical. The dip is slightly shallower, but certainly within the uncertainty. So another thing we can do to constrain the slip orientation is to look at the tidal modulation. So in particular, we're looking at how consistent the event rate is, how consistently it's changing with the modeled tidal stress on the fault orientation that we're considering. So this plot on the left, it fixes the strike to the alignment that we see from the LFE hypocenters. We think that is quite reliable. It allows the dip to vary from 35 to 55 degrees because that's less certain. And then it looks at, as a function of rake, the y-axis here is the tidal modulation slope, which is essentially how strongly the event rate increases with increasing modeled tidal stress. And what we find is that the best fitting point here is for a dip of 40 degrees and a rake of 180, which is pure right lateral strike slip motion, even though it's on this dipping fault. Okay, so if we compare that to what we got before, here's our tidal modulation focal mechanism. Here's the focal mechanism derived from our P wave first motions by comparing with those small earthquakes. And we could compare that to the theoretical focal mechanisms that we would get considering these different types of plate motion. And what we find is that there's a clear winner. The LFE slip matches what we would expect from the relative motion between the Gorda plate and the Pacific plate. So that essentially, that is consistent with what we would expect from this captured slab hypothesis rather than the slab window. So what that means is that the LFEs on the south side are moving with the Pacific plate. So that's the model here of the Pioneer fragment is attached to the Pacific plate. This view is basically looking from the east with north to the right. So yeah, the Farallon, this fragment of the former Farallon plate has been captured by the Pacific and it's being dragged northward and it's essentially trailing the Gorda slab as it also moves northward and as it subducts. So that's pretty interesting. It also means that this low velocity zone is apparently moving with the Gorda plate, which is also kind of weird. So what's happening there? So this is a slice, again, at 27 kilometers depth, which is kind of the average depth of the LFE sources. So it appears that this low velocity zone is essentially accreted to the Gorda slab. It's lower velocities than we would expect for the Gorda slab itself. But why is it there and why would it be moving with the Gorda slab? So this is admittedly a bit speculative, but this is our hypothesis. We think the answer to this may come from looking out by the coastline here, and that essentially compression from the Pacific plate may lead to this effect. So this is a pretty interesting spot because you have the San Andreas here coming in from the south, but then so this is the western edge of North America or North American plate. But then to the north, it steps over and the edge of the deformation front is farther out to the west. So you have this zone in the middle where the Pacific plate is moving northward. This is an old, cold, very strong plate. And it's essentially a bulldozer. And that zone, the Gorda plate, is partially moving out of the way because it's moving to the north. But the piece of North America is really just sitting there. So what may happen, the Pacific has this extreme compression of the upper part of the North American plate, the accretionary prism zone there. And really the only thing it can do to escape this compression is to start subducting, because the Gorda plate is moving, it's moving more north actually than it is east. So perhaps essentially a piece of the North American accretionary prism gets cleaved off and starts subducting with the Gorda slab. And this is actually consistent with the seismicity that we're seeing on this right panel. In particular, this can lead us to reinterpret what happened in the 1992 magnitude 7.2 Cape Mendocino earthquake. This was a pretty interesting earthquake. Shortly after the event, it had the moment tensor for this one it's a little hard to see, but it's a low angle thrust mechanism consistent with what you would expect for subduction. And this was initially interpreted as being a subduction interface event. However, later, as people got more data on where the earthquakes were, people went back and said, hey, wait a minute, this can't be the subduction interface because it's 10 kilometers above where the subducting slab is itself. In our model, we're saying, yes, it is 10 kilometers above the subducting slab, but perhaps this is the location of the main subduction thrust fault in this location. So it effectively reconciles those two different hypotheses. And there are other aspects of this that make sense as well. For one, the deformation front kind of bends around to the east at its southern edge here. And so it's really too far east by the time you get to the southern edge here for this deeper slab seismicity to project to the deformation front. However, the shallower band, consistent, about 10 kilometers above where the slab itself may lie, the shallower band does plausibly project to the deformation front. So we think it's likely that the magnitude 7.2 1992 event did occur on the main subduction interface fault. And that low velocity zone that we see to the north of the LFEs may originate as part of the accretionary prism that's been cleaved off and subducted. So it's kind of like a tectonic hot potato. This material started on the Gorda, it was scraped off and onto the accretionary prism, and then sometime later it was cleaved back off, stuck again to the Gorda, and subducted. Okay, so we think there are a few different seismic hazard implications of this model. I mean, the elephant in the room is this hypothesized detachment fault that would lie, east of the San Andreas Fault. This is not a fault that's in any of the seismic hazard models or other fault models that I'm aware of. We don't see any, modern day microseismicity on it, but that doesn't mean that it couldn't potentially be seismogenic. So it's something that should be considered in future models. This implies that there may be a shallower subduction interface at the very southernmost end of Cascadia. So perhaps we should expect to see more events like the 1992 event. And this, a more extended zone of contact between the Pacific and the Gorda plates might increase the likelihood of Cascadia-San Andreas interactions. I think this is something that, people should look at more through modeling. But, there was this recent paper by Goldfinger et al. Proposing that large earthquakes on the northern San Andreas Fault may tend to follow Cascadia subduction thrust, Cascadia megathrust type events. And this isn't just a Mendocino Triple Junction problem. There has been this idea out there for decades that that there may be a captured slab structure beneath the Bay Area and beneath Central California. So perhaps this is something that that we should look into more, again, in light of what we're seeing at the Mendocino Triple Junction. Okay, so just a few takeaway points. First of all, let's not dismiss tiny earthquakes. Tiny earthquakes, you know, sometimes they're really the only way to see features of tectonics, that we can't always sit around and wait hundreds of years for big earthquakes. The tiny earthquakes are happening now. They're happening in lots of places, and it's worth doing what we can to look at those. We find that the Gorda slab is likely bordered to the south by this Pacific captured Farallon slag fragment, the so-called pioneer fragment, rather than by a slab window. Subduction bounding faults may not follow the petrologic slab boundaries. I think this is an important point that people often overlook. You know, we have these models of subduction zones, and we tend to think of it as one and the same, whether it's modeling the slab or whether it's modeling the faults that accommodate subduction. And what we found is that, at least at the Mendocino Triple Junction, these two may be distinct. And yeah, the captured slab surface would form a large detachment fault. This is something we should think about in future seismic hazard models. And finally, you know, once we have these waveform templates, we can actually do a pretty good job monitoring these tiny earthquakes, and they may reveal variations in slip rate behaviors that we really can't see any other way. So I think it's worth considering how we can do that in a more systematic way. Thanks very much. That's all I have. Happy to take questions.
Thanks, David. Yeah, we are now open to questions, and we encourage questions from students first.
Great talk, thank you. I guess I have a question about the designing your match filters. So you have to design. Do you find that you see variations in those designs?
So which part of the design are you talking about? Like the timing or the station selection, or? Yeah. So let's see, I'll go back here. Okay, so when we have something that looks like a disaster like this, there is a little bit of offset you can see here. So I put in a candidate location that's based on where the tremor location was that was associated with this. So we started with a tremor location. We can compute what we expect the time delay to be at different stations based on that. And so we can make our window vary in time with that. Now, sometimes, you know, after we do this first step and we stack events, we can refine the timing based on what we're actually seeing once we can start to see some of these arrivals. But it's sort of just getting an initial foothold in this data. As long as it's close, it can be good enough. Were there other aspects of the design, or does that answer it? How do you choose which part? Yeah, so I'll be honest, I think I chose a bunch of different parts. I probably chose this part first because it looks higher amplitude, just before the blue. And you can kind of see how well it correlates with other parts of the data. And sometimes what we see is that the higher amplitude pieces of data correlate worse, probably because there are multiple kind of overlapping LFE sources within that. And it's actually better to have time period in data that's simpler, even if it's a little bit noisier from, even if it's lower amplitude. Okay. Yeah. So I think, one thing I probably didn't make clear in the talk is that we don't know where the eastern edge of this slab fragment might be, but it might be not all that far east. And so even if you have this little fragment kind of on the western edge, you're still going to have perhaps some kind of a slab window farther east. And, let's see if I have the plot, but essentially there's the Bartlett Springs Fault, the Makima Fault. The Bartlett Springs kind of aligns with the eastern edge of where these LFEs are. And we don't know if the LFEs cut off because that pioneer fragment ends there, or if maybe it extends farther east. But I think that's the answer to your question.
Related, when you look at the earthquakes in the overriding plane, roughly in the region that has the red circle there, and you do a cost of summation or something like that, there's an interesting position, like these shears are bending around doing weird stuff. And I wonder if your model says something mechanically that would also speak to this potential for Cascadia, San Andreas action, in terms of the mechanics of this sliver that explains that strain field, if that's something you looked at, or is that too far away?
You're talking about the low velocity zone?
I'm just talking about overriding plate seismicity.
Yeah.
And then you look at focal mechanisms for stress or strain rates from them from cost of summation. And then I'm always staring, like, I totally agree, right? It's a keystone region. And I'm like, why does it curve? When does it feel the pull of the subduction zone? When does it lose the shear from the eastern cover from the shear? Something like that.
Yeah. Okay. Well, that's
looking at cost of summation. Is there something in there that tells me something about the mechanics of this?
I'll probably have to talk to you more about that. I don't know. I will say that there's kind of different layers of seismicity. This zone here is deeper than most of the crustal seismicity. It's 20 or 22 kilometers deep. All of the other there's this one weird zone here, but most of this seismicity is 10 to at most 15 kilometers deep. So there do seem to be different things happening at different depths, and you wouldn't want to just combine everything together because I think it would give you a confusing result, because we're seeing there's different stress regimes at different depths, I think. So yeah, I probably need to talk to you more about the details of your question.
I have a question about the seismicity. What's the focal mechanism of seismicity? Are they the same as LFEs? If not, why?
Yeah, this is weird. Let's see. Do I have the plot? Okay, I didn't talk about it, but it's a little hard to see. But there's a few example mechanisms from that zone of seismicity. And there's two things. None of them are the same as the LFEs. And there's a variety of mechanisms they're mostly normal faulting, actually. But you know, there are some that are kind of north-south extension. There are some that are kind of east-west extension. They seem to be, let's see. You can kind of see here, I mean, the projection is a little weird, but these tiny earthquakes, they don't seem to be on this same fault as the LFEs, again, because they have a variety of mechanisms. They seem to be more like kind of a tear faulting that is on, you know, maybe just above where this interface is. I don't know if it's because, you know, there may be fluids coming out of this zone. But they are weird and they don't illuminate a single fault, I guess. It's more of a complex kind of en echelon structure with a variety of mechanisms.
Thank you so much. Yes, slide you showed 20 kilometer microseismicity. So I was wondering what is the magnitude and is there any special equipment for measuring those microseismic events large depth? And so I come from petroleum engineering side, so
Yeah.
they have very close to the event monitoring, like a few 100 meters or feet away from the microseismic cloud. But I was wondering if you have deep monitoring in this case.
Yeah, so there's no deep monitoring. There are a few shallow borehole seismic stations in this area. But these events, the earthquakes are up to magnitude 3. So they're a lot bigger in amplitude than the low frequency earthquakes. And they're big enough that many of these earthquakes have unambiguous P-wave first motions, which makes it possible to do the kind of analysis that I'm doing. I'll say one feature of this, you know, this zone, the micro seismicity of the earthquakes, is that this seismicity zone shows up in every single paper you look back at, you know, back to the 1980s. It's a really persistent zone. It's not just one little swarm, although it has been referred to as the Garberville swarm because of its location above the town of Garberville. But it's, you know, it's a pretty intriguing zone in its own right. And I think, you know, it would be interesting to understand more about the seismicity that's happening there as well. Yeah, the earthquakes.
This is a question from Zoom. How do we correlate the earthquake with tides? Shelley,
So yeah, the low frequency earthquakes show, I mean, I guess the first observation is that they show kind of recurrence times that tend to align with the tides. So that's what these peaks are showing here. And then we can take advantage of that. So essentially we're seeing more low frequency earthquakes at times where the tidal stress is encouraging that slip. And so that's, you know, what we can take advantage of in this part of the analysis where, you know, depending on the fault orientation that we're testing, we can model the stress on that particular fault. We can see whether we expect that stress to be encouraging slip, and we can find the alignment of the fault that optimizes that relationship. So that's what we're doing in this analysis to get another constraint on the slip orientation of the low frequency earthquakes.
Since we are on this page, I have one question about that. So I think, if I remember correctly, the focal magnetism you got from the focal magnetism analysis, the dip is like 34 or something.
Yeah.
So you started the range here from 35 to 55. Is there any consideration of not including, like, say, starting from 30 to start the search?
Yeah. I mean, the other piece of evidence we have is the alignment of the LFE hypocenters, which was more like, I think 48 was the best fitting alignment for those. So we were trying to test, you know, things in kind of that range. Yeah, we could have gone to 30, I suppose. But you can see, I think, 35 does have this peak here with left lateral slip. It's not quite as high as the peak associated with the 40-degree and right lateral slip. But we have other constraints that, left lateral slip doesn't really make tectonic sense in any way that I could figure out. So, and it clearly conflicts with the mechanism that we got from the P wave first motion. So, we're trying to bring in multiple constraints, and this was range that seemed most likely to test.
I have a second question, which is related to Shelley's question. So the microseismicity that is just adjacent to low frequency earthquake. Horizontal view, you can see that they are distributed along the low velocity zone as well.
Yeah,
and vertical profile, they're also close. I know you just mentioned the focal mechanism of them are totally different from the LFEs. But what makes them like regular seismicity instead of LFEs, given the the close proximity between them?
Yeah, that's a really good question. See, I'm trying to find the figure to wave at here. Yeah, why aren't they LFEs? I think that's a question that we don't fully understand the answer to. They're here and in other places, I think we see LFEs that seem to be occurring on these, high slip rate plate bounding faults. And the microseismicity, again, using the focal mechanisms as part of the evidence here, they don't seem to be directly on this fault. They seem to be, reflecting tear faulting or something similar just above that. I don't think we fully understand, why we're getting those two kinds of behaviors so close together. Why do we not see LFEs just down dip of the micro earthquakes? Why are they adjacent rather than just down dip? These are questions that we would love to know the answer to, but we aren't there yet.
Do you think it might be like further subduction, so the temperature and pressure, temperature, and fluid content just favor the currents of LFE like that spot?
Yeah, that's certainly possible. We see, like I showed along the Cascadia margin, there is a certain band where we see prominent tremor and LFE activity, a certain depth range, presumably a certain temperature regime. So yeah, it may just be that that's the spot that satisfies those types of conditions. But again, we'd love to know more about exactly what those mechanical requirements are.
Thanks. Are there any more questions?
Thank you. Early on, you showed that really striking Cascadia tectonic tremor, just that super broad zone that stretches all the way up Cascadia, and then you zeroed in on this sort of anomalous region.
Yeah.
Now that you've learned so much about this anomalous region, does that tell you anything else about that broader tremor zone, or is everything kind of figured out there? Yeah, this is incredible. I mean,
yeah. Well, I think this idea of comparing the LFE waveforms with earthquake waveforms might be effective in other places to try to get focal mechanisms. Now, some focal mechanisms have been estimated, mostly in the northern Cascadia, I think, where the tremor is higher amplitude, and maybe you can see those first motions or model them better. I think most of the results in Cascadia have shown slip consistent with what you would expect for subduction interface kind of slip, thrust fault motion. But like anything, I imagine if we look in more detail, we would see some interesting variations. I think a previous study showed a hint of tremor that had some weird behavior at the very southern end of the main zone of tremor in Cascadia. So maybe, if we could get a focal mechanism for that, we could understand better what's going on with that activity as well.
Thanks.
Okay, I think it's about time. Let's thanks David again. And thanks everyone for joining us.
Thank you.
Sean led the
Yeah.
lunch, so you want to go ahead and.